really super important definition that you're going to use a lot, both in grade 11 and in grade 12, is the idea of a reference angle. So we have angles in standard position, and every single angle in standard position has a reference angle. And what a reference angle is always the angle with the nearest x-axis. So here we can highlight the whole definition, is the acute angle with the nearest x-axis. And one thing I'd like you to add here, above acute, is reference angles are always positive. So if you had an angle in standard position of 35 degrees, then you would ask, well, how far away is this arm from the nearest x-axis? How far away is it? And that's your reference angle. And we write a reference angle with a tiny, that looks messy. I'll try to make it really neat. Okay, so if we have the angle and we call it theta, then we put a tiny little r as subscript, and that is how we label a reference angle. All right, so if the angle in standard position is 35 degrees, this isn't going to be rocket science or anything. There's no trick to this. How big is this angle back to the nearest x-axis? 35, right? Does that make sense? That if you went 35 degrees to an angle in quadrant 1, if you went back to the same positive x-axis, your reference angles in quadrant 1 are always the same as the angle. But if I went to quadrant 2 and I took 145 degrees, now my reference angle to the nearest x-axis is this one. Does it make sense, the math that they did to figure that out? If you knew the whole thing was 180 halfway around, and you already know this part is 45, does it make sense that you would want to subtract the 145 degrees to get your reference angle of 35 degrees? And if they told you the reference angle was 35 degrees and it was in quadrant 2, then you could say, well, 180 minus the 35 would leave me with the angle that's left. So don't look at your notes right now. Look just at the screen, because it's already in your notes. If I went in standard position and I went to quadrant 3 with a reference angle of 35 degrees, what would this angle be in standard position? Can you do the mental math to figure that out? In other words, we're trying to figure out this angle here. How big is that? 215. 215. And what did you do to figure it out? 180 plus 35. Right? Halfway around is 180. And then you're just going another 35. So quadrant 3. Oh, no. We get us 215. What about quadrant 4? What mental math thing could you do to figure out that angle?
Is it 325?
It's going to be 325. What did you do to
360 minus 30?
Right? See, to use the 30, you have to go all the way around to 360, right? And then you can subtract the 35. So we get 360 minus 35 is 325 degrees. Now, we are going to start extending your ability to do trigonometry. Okay? So far, trigonometry has only been SOHCAHTOA. And sine and cos and tan, you've only done them with right-angled triangles. Can you draw me a right-angled triangle where one of the angles is 145 degrees? What's the problem with that? Why can't I do that? Let me just try. I'm going to draw a right-angled triangle I'm gonna make one of them 145. Just did it. What's the problem? What's the problem with that picture? Yes.
Two angles have to add up to 90, so the other one has to be a negative.
Yeah, okay, so if it added up to 90, you're right, I'll just subtract negative 55 here. Doesn't that work? You know, like negative angles, no, they don't make, in triangles, they don't make sense at all. So we don't have any SOHCAHTOA possible with 145 degrees. However, watch the following. We're going to take out our calculators, and I want you to fill out, here's the quadrant 1 box. We're going to do sine of 35 degrees and write out to 3 decimal places, cos of 35 degrees to 3 decimal places, and tan of 35 degrees to 3 decimal places. And we're going to put that in a box. We're going to go to our calculator. We're going to do sine of 35, 0.574. To 3 decimal. We're going to go to our calculator. We're going to do cos of 35. And all of these ones would be possible, 0.819. These are all possible in triangles, right? This is totally possible with SOHCAHTOA at right angle triangles, 35 degrees. And tan of 35. And what the calculator is telling us when we do this is it's telling us a ratio. Ooh, that's pretty. Decimal. 0.700 to 3 decimal places. It's telling us ratio. So I'll take that tan one. That means if I were, I'm going to erase a little bit of stuff here. If I were to make a triangle with the 35 degrees, a right angle triangle here, the tan one says that the opposite over adjacent should be close to 0.7. If I change 0.7 to a fraction, that's like close to 7/10. So it could be that this triangle has a 7 and a 10 there. Or it could be a 3.5 and a 5. Or it could be a 14 and a 20. Any kind of ratio that makes about 0.7. 70 over 100. If I go to 3 decimal places, it's really like 700 over 1,000. The triangle could be bigger or smaller, but the ratio of the opposite side over the adjacent side, that's the power of trigonometry, will be the same. So it could be that that's the size of the triangle, or something bigger or smaller proportionate to that. This is the power of trigonometry. But now, we're going to find out, we'll switch to green. I'm going to go to quadrant 2. I'm going to do sine was first. Sine of 145 degrees, cos of 145 degrees, and tan of 145 degrees, because we are going to try to figure out why reference angles are so important. Okay. Type those into your calculator. Tell me what you get. To 3 decimal places. Put a box around this too. Tell me if you see anything intriguing, interesting, weird. Where's your calculator? Yeah, where's your calculator? Like, it's very hard to know what's put in there. Oh, we didn't too. Oh, yeah. My scientific calculator that doesn't need charging, I forgot.
Yeah, the solar thing.
Okay, what did you get for the first one? 0 point?
574.
574, interesting. Cos? Anybody get that one? Negative 0.819. And tan? Negative 0.700. I can't, it's weird, okay? Good. At least acknowledge that it's weird.
This is like an off-topic question, but like, what is like the sign and the cosine and like the tangible, like what do they actually do, like in math, like when you put in your calculator?
Okay, so what they actually do is someone took and drew out, well, this is not exactly what happened, but if someone took perfect right angle triangle and they drew a 35-degree perfectly, and then they took a very, very, very accurate ruler, okay? And they measured this side, and they measured this side, and they measured this side. They could have found the following. They could have found that this side was really close to 7, this side was really close to 10, and this side was really close to the square root, a squared plus b squared equals c squared, 149. Okay? And when they said, what is tan of 35 degrees? SOHCAHTOA says tan is always the opposite side over the hypotenuse. So if they measured 7 and 10, what is 7 divided by 10? Pretty darn close to 0.7, eh? Of course, they would have said, all right, they probably measured it even closer. Okay? What is opposite 7 divided by the square root of 149? Because that's what I got in my triangle now. Your calculator has it built in. Look, I got 0.573. What does the calculator tell me? 0.574. Because my 7 and 10 isn't like super accurate. If I wanted an even better one for 35 degrees, I could measure it and use millimeters. And then go to like a whole bunch of decimal places. The closer I am in my measurements, the better the ratio is. And if you would do 10 divided by the square root of 149, that should be what cos is. And look what 0.1819, look at that. That came out 0.819. So if someone took, and this is true, if you took any triangle and actually made a perfect 35 degrees and went straight down and took a new measurement, right? Maybe you measured, right? Let's say you measured this to be 3 centimeters. You would measure this side to be about 4.28. And if you do 3 divided by 4.28, you get really close to 0.7 again. And it doesn't matter how big or how small the triangle is, if that's a 35, you will always get this relationship that this divided by this is close to 0.7, no matter how big or how small. Now, your calculator has everything built in, every single angle perfectly memorized, all of those ratios. So it goes back historically, someone has figured out all of those triangles, what those ratios are, and we are now able to use them to figure out all sorts of math problems. Like it used to be, like prior to calculators, someone would have figured these all out. There we go. There's one. And they would print books with all the numbers your calculator can spit out. This book is just numbers over and over again. Oh, is that a bookmark? I hope it's a $10 bill.
Like slid under the recycling bin.
Okay, we're gonna find out. It doesn't look like a $10 bill, but that would have been exciting.
Lisa, did you have to use that book?
Oh, it's that it was part of the Red River College originally. You know what's super cool about this book? It's a signed copy. From Georg Vega. who wrote this book by Baron von Vega. This book published in, let's check it out, This video has a lot of stuff in here that you don't need, right? It doesn't say the date. Okay, but the first table of this kind was published in 1792. And then what happens is someone takes the 1792 version and makes it more accurate. This version was famous because it went to 7 decimal places, whereas the previous version only went to 6. And now your calculator has all of those built in. Okay, check out. So that was a good question. That's basically your question, what is trigonometry? That's the idea of trigonometry. Super powerful, and everything we do goes back to that idea. Okay, new color, quadrant 3. In quadrant 3, the angle was 215 degrees. Before you type them in, we're going to do some guesses. Any guesses what sine of 215 degrees is? You get first guess. Look for patterns, see what you think.
For sine, it'll be negative. Wait, no, it'll be positive 574.
Close! Very close. Second guess.
Negative.
Perfect! You did that without your calculator. That's amazing. Okay? Alright. You got a guess for cos.
Negative 0.819.
Negative 0.819. Correct. Alright. Adam, you're guessing next.
Positive 0.700.
This one's positive. You're right. What? Oh my goodness. You just got lucky. Great. We know you just got lucky. And one more. Quadrant 4. Now we're going to do sine of 325 degrees. Cos of 325 degrees. And tan of 325 degrees. See if you can figure out, I think the numbers you're good at. I think you figured out a pattern with the numbers. I'm amazed with you. But it's whether you can figure out the pattern with the positives and the negatives.
I'm gonna guess negative, positive, negative.
Negative. Yes. Positive. Yes. Negative. Yes.
Oh my god. Why?
Why? That's a good question. That's a really good question. Okay. So first thing, the reason reference angles are so important is because if you know sine, cos, and tan of the reference angles, which we can totally use regular triangles for, you now are allowed to do sine, cos, and tan for angles above 90. So here's an example of one that you can do without your calculator. See if you can figure out how you could tell me the answer to this. You're not allowed to use your calculator whatsoever. What is tan of 135 degrees? It's a little tricky. It has something to do with the reference angle. So maybe the first thing you should do is see if you could figure out what's the reference angle for 135 degrees.
is 45 degrees?
The reference angle is 45 degrees. Nice. So now how can we use that to help us figure out tan of 135 degrees? Do you know tan of 45 degrees? What is it? 1. Okay. Now we're in quadrant 2 though. What do you think tan of 135 degrees will be? -1. Amazing. So, I'm going to teach you the easy way to remember the positive and negative thing. And the easy way to remember is something called, I don't know if it's officially called this, probably has different names. The cast rule. It's called the cast rule because it's like, it spells the word cast. It could have also maybe been called the axe rule, the sact rule, the cast rule, the astica rule, but somehow cast stuck. But if you wanted to start with the astica rule, if that's easier for you, perfect. The only reason we use the word cast is to tell you that you have to spell the word cast. Now, each of those letters represents something that's going to help you. For example, what do you think the S stands for? Sine. So if the S stands for sine, why did we put an S in quadrant 2 in the green one? Because sine is positive. Okay. What about the T? What do you think the T stands for? Tan. Why did we put a T in quadrant 3? Because tangent is positive there. The other ones are negative. Okay. I'm going to guess you're going to figure out what the C is. Cosine. Because cosine is positive. The other ones are negative. What do you think the A stands for? All. Because which ones are positive? All of them. So the cast rule tells us where things are positive and where things are negative. And it's called the cast rule, just so you can spell it quickly. But by just doing this one thing, right, tan of 135, you would say, I know my reference angle is 45 degrees, so I know my answer is going to be 1, but 135 is in quadrant 2, and according to my cast rule, only sine is positive in quadrant 2, so tangent would have to be negative. Give you one more to see if you're doing mental math. How about sine of 210 degrees without a calculator? You might have to look at your special triangles because I'm pretty sure you haven't memorized them that well yet. What's your reference angle?
30 degrees?
30 degrees is the reference angle. Is 30 degrees one of your special triangles? It is. What was the opposite over hypotenuse on the 30 degrees?
It was root 2 over 2.
Oh, close. That was for 45.
Oh.
Yes. Opposite over hypotenuse for 30 degrees because we're doing sine. 1/2. Where is 210? Which quadrant? Quadrant 3. Should I make it positive or should I make it negative? Negative. Beautiful. And the reason we do this and the reference angle is because if we go back to our pictures here, and I draw a triangle in quadrant 1. If I go back to my nearest x-axis, can you see that that's the exact same triangle just flipped over? But all the sides and angles would be the same. And same thing here, if I draw back to the x-axis with my reference angle, same triangle. So all my sine, cosine, tan, all my sides, all my angles are the same. Draw a straight line back here, same triangle, just flipped around. And this is how trigonometry works for angles beyond 90 degrees. It's just the same triangles, but now they think, well, if I drew a triangle in this quadrant, does it make sense that my x-coordinate is technically negative because I'm going backwards? My y-coordinate would still be positive? And if tan is opposite over adjacent, now if positive over negative, tan should be negative. Your hypotenuse is a squared plus b squared equals c squared is always positive. If you did cos, you have negative over a positive, negative. But if you did sine, you have positive over a positive, stays positive. So a little explanation of trigonometry. Your important thing is to realize how important reference angles are. You need to know how to find them. It's always back to the nearest x-axis. So they've got some more examples here. We're going to end our video here. But if you had 155 degrees, reference angle is 25 degrees. 235 degrees. Oh, I've got some questions here, yeah, for you to practice. Question circle 3, 4, 5, and 7.
Wait, so that means the 7 is both? Is it? Oh no, it's the same section. It's the second one.
Awesome.